All right, here we go, guys. It's the last one. This is the last lesson of the entire Chem 1 curriculum, so this is how we wrap it up. Something called Le Chatelier's Principle. Sounds French. Sounds lovely. When you say it, tell your parents, what did you learn about school today? We learned about some French. Right, exactly. We'll talk about what this means when we start to disturb equilibrium. I know at this point in class, most of you guys feel pretty disturbed, so it's perfect for this time of year, right? Like, you're going insane. So anyway, the whole idea of Le Chatelier's principle is that if you have a system at equilibrium, it's balanced and beautifully balanced and everything's all happy, what happens if you apply stress to it? I don't know why I would be talking about stress right before finals, right? Sounds like what you guys got going on. So here we go. Moving on towards Le Chatelier's principle. Oh, by the way, you'll hear this pronounced a bunch of different ways because it's French. So I took French class in high school, so I know actually how to say it right. A lot of people will pronounce this as Le Chatelier's principle, kind of like Le Chatelier's, but Le Chatelier's principle. And if you're American, you might just pronounce it as Le Chateliers, which is fine too. So you'll hear me joke about calling it Le Chatelier's principle, because sometimes you get tired, and that's just all you can say. But it is pronounced Le Chatelier's or Le Chatelier's principle. So anyway, all those pronunciations are fine. As long as you can recognize it, we'll be all right. So here we go. I'm going to use an example of instead of a leaky bucket, I'm going to talk about a fish tank here to represent what's going on at equilibrium. It's kind of the little metaphor that I'll use to help you sort of picture what's going on with these disturbances that we're talking about, these stresses. So imagine that we have, this would be kind of cool, I want one of these. Imagine if you had a fish tank, or two fish tanks that were side by side and connected by little water bridges. So you have a little water bridge up here and a second little water bridge down here. And the second thing we're going to use in this is going to imagine that these water bridges are one way only. So fish can only go to the right through the top bridge and they can only go to the left through the bottom bridge. It'd be really nice. And then as you're setting up your fish tank, you take all of your fish and you dump them into the reactants tank. So at the beginning of your reaction, right, your fish tank reaction, you've got all kinds of reactants and zero products. So picture what's going to happen over a few minutes as you let these fish sort of explore their environment. At the beginning, it's going to look like this, but after a few minutes, it's going to start to look like this, right? The fish are going to start to move around, and over time, they will kind of achieve some sort of dynamic equilibrium, where more or less you're going to have equal concentrations of reactants and products, fish on the left and fish on the right. And fish are going to be kind of crossing back and forth between these two bridges. Now, there's a little bit of a problem with this metaphor, and I want to make sure I'm kind of clear this up at the beginning. Equilibrium doesn't necessarily mean you have equal concentrations of reactants and products. You can have equilibrium with very different concentrations. But for the purposes of what we're talking about here, it's a little bit easier to picture an equilibrium that also has equal concentrations. It'll just be easier. It's more the rate of passage is what's really important for us in a real chemical example. And we'll kind of alternate in this video between this fish tank equilibrium and an actual chemistry equilibrium to kind of get that. But again, in this particular case, it's going to be a little bit easier to picture that these fish have moved back and forth, and at equilibrium we have roughly equal amounts of fish in the reactants tank and in the products tank, and they're sort of swimming back and forth as they go. Again, you're generally not going to have all the fish swim to one side. They'll kind of generally sort of equalize themselves out, and that's what we're going to call equilibrium for the purpose of this particular metaphor, this little story that we're going to use to explain this idea. Okay, so here's our non-fishy example. I'm going to use this one kind of throughout this particular thing. We have an equilibrium that's set up here, excuse me, that is a reaction between dinitrogen tetroxide, which is N2O4, and NO2, nitrogen dioxide. So in the pictures up here, you can kind of see the three extremes of this. Dinitrogen tetroxide is pretty much a clear gas. You can't see it at all. These are little sealed containers that contain just a gas. So this one is N2O4, and it's basically clear. This one over here is what NO2 looks like when it's in its purest form, basically all NO2. And it's sort of this reddish brown sort of a color when you see it for real. If we were at equilibrium, and I'm talking about the sort of equal equilibrium, we would have kind of equal quantities of both, and we'd be at this particular situation right here, where we have kind of this intermediate color. It's sort of yellowish looking, but that's kind of that reddish brown 50% and clear 50% kind of gives you this look of basically kind of a yellowish container. This is what's a little bit different between the fish tank example and a real chemistry example, is in a fish tank, we could talk about two different tanks, right? The reactants tank and the products tank. In a real chemical reaction, these are all in the same container. we've got reactants and products in the beaker together. And so it's a little bit, we don't just have them move literally one side to the other. So again, there's a little bit of an issue with this, but it'll still help you kind of picture what's happening in our stresses. So like I said, at equilibrium, in this particular case, you're going to have sort of this yellowish container. We're going to come back to this. This is like our equal fish tanks is our yellowish container like this, our equal equilibrium that's got equal quantities of both of those. Okay, ready? So what's going to happen if we start messing with this? So messing with equilibrium is, of course, kind of the fun part. I know you guys. So this is called the Chatelier's principle. What happens if you disturb a system that was at equilibrium? You can imagine all kinds of things you could do to those poor fish to kind of spook them or scare them or make them do something different, to make them kind of swim around a little differently. So this is called Le Chatelier's principle. Disturbances that we apply, the technical name for those are called stresses. So you apply stress to a system. That's what we're going to call these disturbances. The typical stresses that we're going to talk about today are going to be the effects of changing concentrations, changing pressure, or changing temperature. Those are the three stresses that you're going to need to know how to deal with by the end of this particular lesson. The system will temporarily become imbalanced. So if I apply a stress to it, it was balanced beautifully, and then all of a sudden things are changing. So temporarily, it will no longer be in equilibrium. However, equilibrium is a natural state, and as time progresses, the system will sort of shift, and that's the actual vocabulary word that they use for this is a shift, in order to kind of achieve a new balance. The new balance is going to be in a different place than it was before, simply because we've changed those conditions. So equilibrium will be reestablished. It'll achieve some sort of a new balance, but those concentrations now of reactants and products are going to be different now that we've messed it up. The KEQ will be the same, but the literal numbers that we're entering into it are going to change over time. So we don't have to worry about too much math here. I'm going to actually just about directions, not about numbers in this part. So this is the statement, the kind of the formal statement of Le Chatelier's principle, which is if a stress is applied to a system at equilibrium, the system will shift in order to relieve or reduce the effect of that stress. So we're going to talk about what this looks like now with our fish. So let's say we applied our first stress. Our first stress is concentration. So we're going to talk about some different ways that we can change the concentration of our fish, I guess, in our tank. So imagine our equilibrium tank, here it is, that we have kind of basically equal numbers of fish on both sides. And now I want you to imagine what happens if we start to dump a bunch of more fish into the reactants tank. What's going to happen? So if I start adding more fish to this side over here, overall, what are they going to do? Well, if I dump a bunch of fish over there, this is the stress in the new tank. The fish in general, on average, are going to start to kind of shift towards the right because we've got way more fish on the left. We have less density of fish on the right. And we're going to start kind of shifting over towards the product side. So what this is going to be called is a shift to the right as the fish are swimming that direction towards the product side. And in the end, we're going to have a higher concentration of products than we did before. So again, that's kind of how we discuss these. A shift to the right will cause an increase in the amount of products at the new equilibrium. So let's take, I missed a fish. I missed a couple of fish. Got to fill up my fish. All right, there we go. So again, more fish, shift to the right. Really? How many fish do I have in here? Dang, that's a lot of fish. Okay, ready to go? Okay. What does this look like in an actual chemical reaction? Again, if I add to the reactants side, I add stress to the left, the whole system is going to shift to the right. So let's take a look at how this looks in a chemical reaction. Imagine that container like the yellow one in the middle, our equilibrium container. And if I add more N2O4 into this container, somehow pipe it in there somehow, I would have to have a nozzle or something. But anyway, believe me on this one. Imagine I stuck a bunch more N2O4 in this, what's going to happen? Okay, so let's take a look. I'm going to dump a bunch of stuff in here. So initially, I'm dumping a bunch more clear gas in there, a bunch more fish in the left tank. And that at first, it's going to get a little bit lighter because I'm putting a bunch more of this clear gas in there. However, over time, these gases are going to shift to the right side of this equation. I don't literally mean move, but I mean we're going to shift to the right in the sense of making more products. So as we dump a bunch of N2O4 in there, we're going to actually end up creating more of this stuff, our product, our NO2, and over time, that tube will actually get darker. At first, it will be lighter, but at equilibrium, it will be darker than this original yellow. So it'll be kind of shifted towards this side. I know it's kind of a weird thing to think about that. Again, initial is not what we're talking about. Yeah, initially it's going to get clear as I put that clear gas in there. But at equilibrium, because I've now shifted it to the right to make more products, our end tube is going to be a darker yellow than this one is shifted over towards this reddish brown. Not this brown, but shifted that way. Okay, let's take a look at another example. Anyway, new, darker than the original, I said that already. So what's going to happen in, there's our shift. I wish I knew what I'd actually done. It would make more sense if I'd actually remembered what I'd put on my screen. Anyway, shift to the right. All right, let's take a look at the other side. What if we dump the fish in the other side of the tank? So in this particular one, now I'm adding fish over on this side over here. So what's going to happen when I fill up my right side fish tank? Now my stress is on the right. What are the fish going to do? Okay, now I've got too many fish over here. Now the fish are going to start to shift to the left. I've added the stress, added more concentration to the right side, more products. So they're going to shift more and end up increasing the number of fish in the reactants tank. So eventually they're going to fill up and go that way. So, sorry, if you weren't done looking at the fish, there you go. So what is this going to look like in my chemical equation? Here, what do we got? So this is going to be our shift to the left, right? So here's our equation. I'm going to start with my yellow container, my equilibrium. And if I add more NO2, what's going to happen? So I'm going to somehow open this thing up and dump a bunch more of this and just kind of squirt it in there. I guess it's a gas, so it'll be a little tricky, but what's that going to look like? All right, initially, this is going to get darker because I'm dumping in a bunch more of this brown gas, right? I'm dumping a bunch more products in there. But then this equilibrium, because I'm adding to this side, it's going to shift to the opposite side. So it's going to shift to the left. And that means that at equilibrium, because it's shifting that way, it's going to cause me to actually increase the amount of reactant that I made, this N2O4. And as unlikely as this sounds, at the end, after this is done shifting, it's going to actually end up being lighter, totally counterintuitive, lighter than it was to begin with, because that NO2 that we did is going to end up creating more of this stuff, and it's going to shift towards this direction. So it won't necessarily be a bunch paler, but it's definitely going to shift kind of that way. And again, I know it's completely counterintuitive. Shift to the left, going to get to the paler side in this case. Again, I know it's counterintuitive. All right, ready for the next one? Okay, what happens if we start to take fish out of the tank? Still dealing with concentration now. I'm going to decrease a concentration as opposed to increasing a concentration. So here's my equilibrium tank. What happens if I start to pull out products? So now I start to take my fish out of there. Think about what the impact this is going to have on my equilibrium. Now at this point, what's the stress is a relief of stress. I don't know, it's kind of like a vacuum if you want to think of it that way. So now I've got too much on the left and not enough on the right. So this particular equilibrium, the fish are going to shift to the right. They're going to fill that gap, I guess. Like I said, it's kind of like pulling water out. More water will fill into that space. So we're going to actually have a shift to the right with it. It's going to end up at the end making more products. So even though I'm pulling products out, more products are going to kind of flow that way, and I'm going to actually end up reducing the amount of reactants, right? It's going to flow towards the right. Increase products, decrease reactants. It's going to end up on that particular side. So there's my lonely fish. Again, at equilibrium, that's what I'm starting to do as my stress. They're going to go flow in that way to try to fill up that empty tank. So here's what it looks like in a chemistry sense, right? Here's our same equation that we're talking about. Again, start with our yellow. What's going to happen if we remove from the central container, what happens if we remove from the central container NO2, and just NO2, which is difficult to do, but imagine that that was a possibility that I could somehow pull the NO2 out of this. All right, if I'm pulling NO2 out of this, NO2 is my product, so if I'm removing my product, that means this whole thing is going to shift to the right. Again, I know it's a little bit weird to say that, but if I'm taking product out, the whole rest of it is going to shift to kind of fill that space where I've taken the NO2 out. So again, I'm going to end up shifting it that way. So what is that going to look like? It's going to have a shift to the right towards that product side, because that's where I'm removing product, and that's really weird. So more of that reactant is going to form more product. So in the end, it's going to be changing it to actually make it darker again. I'm going to use up the rest of the N2O4 that was on the left. I'm going to turn all of that into the NO2 as I shift it to the right. The equation is going to get darker and darker and darker. Again, it sounds really weird that I'm removing the dark stuff and yet the container is going to get darker. Counterintuitive, but that's what you're doing. Again, removing from the right, it's going to shift that way. Again, if you press on the right, add to the right, it's going to shift away from it. So it's kind of get this sort of a motion as you do it. So if I'm removing from one side, it's going to shift towards it. If I'm adding to one side, it's going to shift away from that and push to the other side. Anyway, by the time you're done with this whole thing, you're going to end up with an increase in the amount of NO2 that's being produced overall as I keep pulling out, and a decrease in the amount of NO2 or N2O4 as that stuff is getting used up. Again, shifting away from the left, shifting to the right. All right, last one. Oh, there's our big shift arrow. It's going to shift to the right. So what's this going to happen if I do the other one? I'll kind of let you stop and think about this for a second. I didn't do another fish slide on it because I think maybe you could figure it out right now. What happens if I decrease the amount of reactant? So again, in this particular case, start with our yellow container. What happens if I can remove the N2O4? So what's this going to do? All right, think about it. Got an idea? All right, if I'm removing N2O4, I'm removing reactant. That means our equilibrium is going to shift towards that side. And in the end, what's that going to do? It's going to end up away from the NO2. We're going to use up the NO2. We're going to transfer it into N2O4. So with this one, our initial effect is going to be a shift to the left. It's going to, because we're removing a product, we're shifting away from that. Or removing a reactant. Sorry, it didn't change that. Our new equilibrium is going to end up being lighter. Again, counterintuitive. We're shifting to the left. So we're using up our NO2. And we're going to be creating more N2O4, which is our lighter gas between the two of them. It's going to shift that direction. Again, it's going to look like a lighter colored gas. Again, it's kind of weird. Don't worry too much about colors if that's kind of freaking you out. You can just kind of say shift to the right, shift to the left. Sometimes it's just nice to see it. I will show you a demo in class, by the way, that has kind of a color shift like this. So that's why I wanted to put a color shift example in our lesson today, because that's kind of what we'll show you in class. It's just easier to see it as opposed to just do it on paper. All right. Stretch number 2, changing pressure. A little bit different than what we're doing with our what we did before, but kind of a similar-ish sort of idea. Imagine that I'm changing the size of my fish tank instead. So this is how I'm going to change my pressure here. This example doesn't work as well, but you can kind of imagine kind of what it's going to happen here. So you can't really change the size of the tanks very easily, but imagine that if I had these happy fish at equilibrium and the right side tank all of a sudden got to be half size, just shrunk without changing the fish. All of a sudden now those fish over on the right are more concentrated. You think about the number of fish per liter, right? It's our concentration of our fish. They're at higher pressure, higher density, higher concentration. So this is very much like changing a concentration problem. So which way are these fish going to go? Well, all of a sudden these fish are in this little tiny container, so they're going to swim towards the side that has less concentration to it or less pressure to it in this particular case. If I increase the pressure to it, they're going to kind of shift over to the other side, to the more comfortable side where they're going to fit better. So this reaction doesn't work as well. So let me give you an example of what this looks like with actual chemical equations. All right, so chemical, come on. Move on. Oh, I'm increasing my fish as they go over to the left. There we go. All right, so what happens here? Okay, again, this is going to be what happens if we change the pressure of the container. Now, this only applies to gases, and I'm only going to give you a question with this that would have gases in it, not like a trick question or anything like that. You can't change the pressure of a solution, so it doesn't really apply there. So imagine a container like that middle one, the yellow one, and all of a sudden I made it smaller, half size, like somehow took all of that gas and crushed it down into a little bitty container, which effectively increases its concentration. So unlike the fish, again, I can't just make one side of the equation smaller or the other. Everything's in the same container. I've only got one container. I got to crush everything. It's not like the reactants are in one container and products are in another container. It doesn't quite work like that. We get a little bit of a problem here. So I'm crushing this whole container down. They're all mixed up together. And this kind of changes how we have to interpret this. There's a rule for it, so let me give it to you in a second. But when we take that container and make it smaller, that means we have more pressure inside that container. A bigger container has reduced pressure. A smaller container has increased pressure. And in terms of the equilibrium, here's the rule. Again, it's not as clear as the fish example is. So this is the rule that you have to memorize. But with equilibrium, the equilibrium will shift to the side with fewer molecules when you have higher pressure. Now the reason is if you take a look at our equation here, we've got different number of molecules on there on our two sides, our reactant side and our product side. If you have a tiny little container and you have a choice between the reactants that have fewer molecules or the products that have more molecules, the fewer molecules are going to fit in that small container more easily. They're going to be more comfortable. It's not really the term, but they're going to be more comfy in that smaller space. If you have a great big space, then you can put all kinds of molecules in there. Tiny little space, you want the least number of molecules possible. That's going to relieve the stress. So let's take a look at what that looks like in this particular container. So if you look at our chemical reaction, you got to look at this closely, and I know this is different than what we've done before. On the left side, our reactant side here, there's one molecule that's formed. It's one molecule of N2O4. Notice I'm using the word molecule, not atoms. There's one molecule of N2O4 that's on the reactants side. On the product side, there are 2 molecules of NO2. It does not matter that those are smaller molecules. It doesn't make any difference at all that there's only 3 atoms here and there's 6 atoms or something there. That doesn't matter. It's the number of total molecules. 1 molecule on the left and 2 molecules on the right. So because we're going to a smaller container, this is going to shift to the side with less molecules, which in this case is the N2O4 side, the side with 1 molecule. So it's going to shift that way. So if I squish it down, the container is going to get magically clearer as the reaction equilibrium favors the reactants side in this case because there's less molecules here. Okay, so let's take a look at what we do on the other side of this. What happens when we make the container bigger? Well, it's going to be the opposite side, probably, obviously. But so what happens here? Make it a larger container, make it a double-sized container. Now we've got less pressure, more room, right? So now the equilibrium is going to shift to the side that has more molecules because those more molecules can fit there and bounce around and take up that space, and they're going to be totally happy there. So with this case, in this case, we take a look at it. The side that has the more molecules is the right side. It's the NO2 side because there's 2 molecules present. So again, it's going to shift there. What's important is there's no single rule that says look to the right side or look to the left side. You have to look at the coefficients and count the number of molecules in each equation. You can't just say if you increase it, it always goes left, or decrease it, it always goes right. Look at the equation, so be careful. And finally, if you do have a situation where it's equal on both sides, kind of the trick question, like there's 1 molecule on the left and 1 molecule on the right, changing pressure will have no effect. Because it's equal, it won't make any difference. It won't change the equilibrium point at all. But that's kind of a trick question. So again, decrease the pressure. It's going to go to the side with more molecules, which in this case is to the right, and that container will get darker and it'll shift to the right. So again, pressure is all about number of molecules. Okay, that's the key point here, not about concentrations. How many molecules are there, left side and right side? Okay, last one. So shift number 3. Stress number 3 is changing the temperature of a system that's at equilibrium. So what would happen to our equilibrium tanks here if we increase the temperature a whole bunch? Which way would the equilibrium shift? It's a bad joke. They'd shift up because they'd all die. So no, we can't use the fish example with this one. Temperature and fish, not nice. We can't make them cold. We can't make them warm. That's not going to work for us. Let's just talk about chemistry. Sorry, bad joke. Okay, so let's take a look at the same reaction that we've been doing before. With this one, notice that this reaction is endothermic. It's been on every single slide, but we kind of have not talked about it until this point. So this reaction is endothermic, which means heat has to go in. Heat is a reactant. It's going into the reaction. Exothermic would have heat written over on this right side, and heat would be a product, right? Heat's being given off. So this particular reaction is endothermic. So what's kind of nice about this is we can treat heat like any other reactant. So if I increase the temperature, in this case, it's like increasing a reactant. So that's kind of one of the nice things we've got. So if we add a reactant, if we add to the left side, right, we're adding to this side, it means it's going to shift over to the right. So we're putting pressure on this side, it's going to shift to the right to relieve that stress, and that means we're going to end up actually causing that more on the right side. We would produce that. By the way, if we remove the reactant, what would happen if we made it cold? Right? If we reduced the temperature, that would be like removing heat. Now it would be lifting up on the left, and that would cause us to shift to that side. So if we removed that heat, it would cause this whole system to shift to the left. It would become more colorless. If I add heat to it, I'm adding to the left side of this equation, right? Putting more pressure on this side. I'm going to shift it over to the right. I'm going to increase the amount of NO2. It will get darker. So then I can just, by heating it up and cooling it down, it's actually what was going on in those other pictures. I don't know if you saw the stuff that was in the rest of that. The N2O4 container was on ice. The NO2 container was in steam. It was actually making it really hot. So they were in hot water. So again, treat it like any other reactant or any other product. So here's the example for you. If temperature is increased in this particular case, right, take a look at what we've got here. Here's ice cubes, and then here's hot water that's in the bottom of this. So adding heat is like adding a reactant. If I add to this side, it's going to shift to the right, which is browner. If I do the opposite, where I reduce the temperature, right, now I'm changing it this way, and there's the ice cubes over there, but if I remove this, shift it up, that means that this side's going to shift towards it, right? And so it's going to shift that way, and that reaction is going to become colorless, and that's whether this one is on ice cubes. And again, I don't know if you looked back, you probably thought those were cotton balls, right? But if you look back at these, that's how they made these kind of sit still like this, so we could see the 3 different colors of that, was by using temperature, because it was easy. Okay? All right. Shift to the left that way. All right. Here's your practice problem for this. So take a few seconds, and based on what we've learned about concentration, pressure, and temperature, take a look at this particular reaction. This is the decomposition of ammonia. We've got 2 ammonia molecules on the left are going to be in equilibrium with 3 hydrogen molecules and 1 nitrogen molecule on the right. This is an exothermic reaction, so heat is a product. Heat is given off from this reaction. So take a few seconds and see if you can jot this down, and I'll go through and do the reactions in a second. But for each one of these, I want you to think about, number one, which way would this shift? Would it shift to the left towards the reactants or shift towards the right on the products? And then what will increase and decrease? Will the reactants increase or decrease? Will the products increase or decrease? So kind of go through that in your head, kind of sketch those out. There's my list of 8 things, and hit pause right now, and I'll come back and give you the answers here. Ready to go? All right, so here we are. If I add ammonia, I'm adding to this left side. That means the reaction is going to shift to the right. And if it shifts to the right, that means we're going to increase the amount of hydrogen and nitrogen, decrease the amount of ammonia that was present. I almost said pneumonia. That'd be weird. How about if we add nitrogen? Okay, adding nitrogen is adding on the right side, so it's going to shift that direction. So it's going to shift to the left. And if we shift it to the left, that means in the end, we're shifting to that side. We're going to increase the amount of ammonia that's present. We're going to decrease the amount of nitrogen and hydrogen that were present in that container at the end. By the time it re-achieves equilibrium, we're going to have shifted over to that side. Okay, how about removing ammonia? So removing ammonia, we're going to take away from the left side. If we take away from the left side, then we're going to shift that way as well. It's kind of the same direction. Adding nitrogen and removing ammonia have the same effect. So if I remove the ammonia, going to shift that direction, and in the end I'm going to decrease the amount of products, decreasing the nitrogen and hydrogen, and I'm going to be increasing the amount of ammonia that was produced over time. Shift to the left. All right, removing hydrogens the other way. I'm pulling up on the right side. So if I pull up on the right side, I'm removing hydrogen. So that's going to shift to the right. So in the end, if I shift it to the right, that means I'm going to have less ammonia. I'm going to have more hydrogen and nitrogen at equilibrium, or at the new equilibrium to it. Okay, so those are the effects of concentration. So the ones on the right now, we're talking about the temperature and pressure things. So how about making it hotter? Okay, making it hotter is like changing the amount of heat that's there. So if I make it hotter, I'm actually adding to the reactant side. It's an exothermic, did I say reactants? Adding to the product side. I used the correct hand anyway. I'm adding to this side over here, the product side. So if I add to this side, it's going to shift that way. So it's going to go that way, all right? Shift to the left. So we're going to pick, there it goes. There's my arrow there. So if I shift to the left, I'm going to increase the amount of stuff that's over here, the reactants. I'm going to decrease the amount of products because this is exothermic. If I made it hotter, it's going to be harder for it to actually do that. It can't give off the heat. It's kind of weird to think about that. So decreasing the amount of products, increasing the amount of reactants as it shifts to the left. Okay? Larger container. So if I make this container bigger, and literally expanding it out, that means I'm going to shift towards the side with more molecules. So you got to look at the equation really closely, look at your coefficients, and find the total number of equations to figure out which one this is. So if I look at my equation, on the left side I have 2 molecules, and on the right side I have 3 plus 1. I have a total of 4 molecules over on the right side. So my products has 4, my reactants has 2 molecules. So if I have a larger container, it's going to shift towards more molecules, which is towards the right. So that means I'm going to be increasing the amount of hydrogen and nitrogen, shifting that direction. I'm going to be decreasing the amount of ammonia that's present if I make the container larger. How about if I put it on ice? Okay, ice is a heat question. So now I'm talking about heat on this side. If I put it on ice, I'm not adding heat, I'm removing heat. I'm taking heat away from it by making it colder. So if I make it colder, remove heat, it's going to shift to the right. And again, if I shift to the right, it means I have less of this stuff and more of that stuff. So it's going to shift that way. I will have a less ammonia, more hydrogen and nitrogen. And then finally, increasing pressure. So if I take this container and crush it down, again, number of molecules is what's important with pressure, so I'm going to crush it down. It's going to shift towards the side that has fewer molecules. In this case, fewer molecules is on the left side of my equation because there's only 2 ammonia molecules as opposed to 3 product molecules. So this is going to shift, I don't know what I just did there, shift to the left as we do this. So again, we're shifting it towards the side that has fewer molecules, so we're going to have more ammonia, and we're going to reduce the amount of concentration of hydrogen and nitrogen that are present. So I know this is confusing, this idea of kind of shifting back and forth. A lot of times when students are doing this on the test, they're literally going like, okay, it's shifting this side, that side. It's kind of normal to do the pantomime as you do it, so that's totally fine. But that idea of shifting, I know is kind of a confusing thing. We'll do a lab on this actually in class, and I'll show you some demos so you can kind of see what this looks like for real. Okay, here you go. This is our last unit of the year. Equilibrium. We talked about what equilibrium was. That equilibrium is when the forward and reverse rates are equal. In this particular example, our fish tank example, I did use an equal equilibrium where we had equal concentrations of reactants and products, but it isn't necessarily that way. Again, it's just easier to sort of picture in our head. So in this case, at equilibrium, the concentrations don't change. But what happens if we do something to it? Now we add some sort of a stress, change the pressure, change the temperature, or change the concentrations of something by either adding or removing something. That's going to take that system that was in balance and now knock it off kilter. And it's going to wobble for a little bit, but eventually it'll shift one way or the other way in order to achieve a new balanced state. And that balanced state may now be shifted to the right, or that new balanced state may be shifted to the left from wherever that original balance was. And that's what we talked about with Le Chatelier's principle, is how do those shifts occur? So number one, see the caption that's on the thing, that's the statement of what Le Chatelier's principle is. But the equilibrium is going to shift one way or the other to relieve the stress. So if I'm adding to this side, the equilibrium is going to shift that way. If I'm adding to this side, the equilibrium is going to shift this way. Or if I'm removing from this side, like taking away, it's going to shift over that way. Removing from this side, it's going to shift over there. So again, it's kind of a weird kind of idea of those shifts. Temperature works the same way that concentration does. Treat temperature like any other reactant or product. It may say the word heat, or it may actually give you a number, like the number of joules of energy they're given off, so don't worry about that. I'll show you some examples in class. The weird one is pressure. And pressure is the one where you're talking about making it smaller or making it bigger. If I make the container larger, it will shift towards the side with more molecules, because that fits. If you go to the one that has less molecules, smaller container, it'll shift to the size that has less molecules. Ooh, looks like I'm almost out of battery. But that's the way that it'll kind of shift back and forth to relieve those sorts of stresses. So hopefully with Le Chatelier's on your part, I haven't given you too much stress. I'm sure that I've definitely added a stress to your brain. I've been adding stress to your brains all term, right? And you guys have been shifting by absorbing and studying and learning and getting smarter, right? I can hope. Anyway, it's been a pleasure working with you guys this year. I really hope that you've enjoyed it, and I will see you in class tomorrow, at least for a couple more days, and then I'll have to see you in the hallways. It's been fun, okay? Bye, guys.